her kind introduction and also for her kind invitation to deliver this seminar today here in the University of Calabria. We will be talking about bridges. We will be talking about the seismic design of bridges and particularly soil structure interaction in the nonlinear range. C'è un eco, no? Ritorno. C'è un ritorno? Just a moment. Secondo me la cosa migliore sarebbe tenerlo a 0 in aula, che non serve, e poi va, tanto va fuori, no? In aula non serve. Io curo questa cosa, perfetto, va fuori, no? Sì, devo parlare comunque qui. Excuse me, just a few technical problems. We will be talking about soil structure interaction, concentrating on nonlinear effects. I'm just starting reminding to most of you the usual method to account for soil structure interaction through a linear equivalent method. Basically, we have an entire system here, complete system, and the common tools for studying soil structure interaction is to decouple the problem, whereby decoupling means that we take several elements of the problem and we tend to analyze them separately. Just having them communicate to each other. So for instance, we study the ground response analysis using a free field soil column, meaning that we neglect the existence, the presence of the structure. Perhaps we modify somewhat the foundation input motion, the ground motion here, by taking into account some kinematic interaction effects. And then the motion computed in this way is applied back to a structural model, and it enters through time histories of displacements and rotations through an equivalent system here, which for soil is made of either concentrated springs and dashpot, or sometimes through distributed spring and dashpot systems. Now, of course, this is a linear system. Especially these are linear rheological elements. But the whole point of the presentation today is that nonlinearity matters. Why does nonlinearity matters? For several reasons. The first of all, I believe, is that we should never forget that before that we studied the seismic behavior of structure, that structure is carrying the static loads. And it is very easy to demonstrate, we are not going to do it now today, but it's very easy to demonstrate that most structures interacting with the soil, they mobilize nonlinearity and in fact the strength of the soil under static conditions. So in fact, the initial condition is an initial condition which the nonlinearity of the soil is already engaged. The second reason is that we are called today to study structures that will be subjected to very strong earthquakes. Not because earthquakes are becoming any stronger, but because we want to be protected also by extreme events. So therefore, the current design philosophy is to design also for these extreme events. And under these extreme events, we must check that damage is still, by certain degrees of judgment, admissible. Computing a damage means that we need to account for the nonlinear behavior of systems, because we must account that of the fact that several members of the system will mobilize their strength, or their capacity. And therefore, this is nonlinearity by all means. We cannot escape from that. And another element is that we need to study interaction between soil and structures, and structural elements do have nonlinear behavior. Now, in some instances, this nonlinear behavior may or may not be engaged. It is engaged, in fact, also in for very severe earthquakes, also in the current structural members. But since we deal with bridges, sources of nonlinearity are especially in the bearing devices that are specifically designed to have dissipative behavior. and sometimes for the nonlinear response of piers, especially when we have a tall piers or viaducts, which will be very slender, and it's not very easy to make sure that they will stay in the linear range. So nonlinearity matters, it is very important. And in this presentation, I will be talking about possible ways to take into account also structure interaction nonlinearity, but I will narrow down the field of structure, the type of structure for which I will be talking. I will be referring to bridges, especially to girder bridges with some element of structure interaction for suspension bridges. And I also will narrow down the type of analysis that I'm going to concentrate with, which is a time domain analysis. Time domain analysis are not the most common time of seismic analysis in engineering practice, but it is becoming rather frequent, especially because of the large availability of seismic record databases. Therefore, it is becoming easier and easier to express the seismic motions in terms of acceleration time histories rather than elastic spectra. And it's easy to predict that in the future, this type of analysis will become more and more spread, if not the most used, but very much more used than now. So we concentrate on time domain analysis for bridges, and most of the presentation I will be talking about this first category, which is the decoupled method. We always need some degree of decoupling in design. These are completely decoupled methods, and I will tell you what I mean by decoupled methods. And in the last part of the presentation, I will show you something a little more complicated or simple in some respect, which means a method to introduce partially some soil structure coupling directly into the analysis. But let's start talking about the completely decoupled method. So here, perhaps you see in this sketch quite clearly what I mean by decoupled method. We still have the seismic motion, which is computed independently from the structure. So it is computed from a ground site response analysis. And then the computed motion at some representative point into our column is applied back to a system where we have a global structural model of a bridge. We are talking about bridges now. And the soil structure interaction is captured by this black box, which is not the blue box here, that is called to represent the essential nonlinear features of the soil structure interaction. We call this box a macro element because it is called to express at a macro scale the nonlinear response of the soil foundation system. Macro elements are not a new idea. This is a seminal work done by Roberto Nova and Lorella Montrasio in the early 90s, whereas they were looking at a small-scale experiment where they had a foundation on sand, and they were loading this foundation using different force paths. So they were looking at the complete soil foundation system as through a single constitutive relations. Rather, they were not looking at the constitutive relation of a soil element located within the soil involved in the interaction, but they were regarded the whole system as at a different scale, at a macro scale, trying to develop the constitutive relations in terms of force versus displacements, rather than as stresses versus strains. And you can see here that way probing the force space, vertical force, horizontal force, moment, they were probing the force space with different force paths to get an ultimate surface and to get the entire force displacement response that they were trying to reproduce with an analytical model, which in this case was limited to static monotonic loads. Now, since then, a lot of ground has been covered, and several macro element formulations have been proposed, which are essentially based on assumption including the plasticity. This is, for instance, a bounding surface plasticity model where the plasticity, again, I repeat, the constitutive behavior is in fact expressed at a macro scale as a relationship between force and displacement. For instance, this is as an assumption about the ultimate limit load for a foundation developed by the research group of Alain Pequet in France. This is a bounding surface formulation. This is the monotonic and cycling behavior, and also some comparison between the complete finite element modeling and macroelement response in a time domain dynamic calculation. So there is a certain number of these macroelements which has been developed over time. However, here we're talking about bridges. Hopefully about the implementation of these techniques for real bridges. And when we come to bridges, there are some peculiarities. And the peculiarities is that most of the time, or very often, I should say, in viaducts, in girder bridges, the foundations have pile foundations, so they are founded on a group of piles. You see here a plan view, for instance, and also big point, girder bridges have abutments, and abutments are intermediate structures because they act as foundation structures because they have to carry the vertical load from the bridge. They sometimes are linked rigidly to the deck, so they carry the horizontal seismic forces, but they also carry the pressure from the embankment, and when it comes to their dynamic response, they are seen to interact quite closely, and the inertial effects of the embankment can be quite significant, can really be responsible for the seismic behavior of these structures. And of course, macro elements for these type of structures are not very well spread. There is only a few proposals and not very convincing. This is why the work done in a group which I have been coordinating over last year have been dealing essentially with the development of macro elements for bridge abutments and for pile foundations. Let me just tell you only a couple of things about this group, which is a very small group. As you've seen, basically is my co-worker Davide Gorini, which is actually the guy that develops everything in this research. I'm here to tell you stories. He's there to, he will tell you his stories, but to do most of the job. And for the work that has to do with bridge abutments, Andrew Whittle for MIT in Boston provided a very substantial help, suggestion, and guidance. Now, I will tell you now what are the basic ingredients of the constitutive behavior that we developed for these types of substructures. I will not enter into the details of the formulation because of lack of time and because I'm not the most appropriate person to enter into the details of the formulation. But essentially, the basic ideas in a one-dimensional form may be expressed by this assembly of rheological elements. This is really an extension of the Iwan-Emroth's model, whereby we have groups of springs and sliders in parallel, and these are connected in series. And then the first spring represented the small strain stiffness of the system. The last slider represented the ultimate strength of the system. In fact, this one-dimensional Iwan-Emroth's model, when we come to a multi-dimensional formulation, using not only a single force component, but all force component, translates into a constitutive model made with multiple yield surface. So it's a Emroth's type, Iwan-Emroth's type model in multi-dimensional force space. Here, at a certain stage of the development, we decided to add masses, which you see there, to confer an inertial behavior to this constitutive model, which otherwise per se will not have any inertial behavior. If we don't have mass, we don't have inertial forces. Now, there are different ways to include the inertial behavior here. One is to include it into the constitutive equations, which is shown here. The other one is to add masses externally, and we tend to do both in this very moment, whichever is simpler. The formulation is done using a hyperplastic formulation, which you may study in the books by Holsby and Padzin. Something in the PhD thesis by Davide Gorini. I will not tell anything more about hyperplastic formulation, but essentially it is a formulation which ensures that the constitutive behavior that we get is thermodynamically consistent. So we do not create or dissipate energy in excess of what we should. I will rather concentrate on which are the basic ingredients of this model and how they can be developed and how can they be calibrated. Now, there is a strong difference between developing an expression and calibrating. I will be showing you how we arrived to certain equations and certain shapes. And of course, what we did is not what the designer needs to do. This is a developing phase. But later on, I will try and tell you briefly what the designer, a user needs to do in order to use this element. So an ultimate force surface in force space can be obtained by several means. We found that the most convenient way to obtain this ultimate surface is using limit analysis, at least for the bridge abutment. Limit analysis which are implemented into a finite element code called Optum, either 2-dimensional or 3-dimensional, which is a finite element application of limit analysis theorem. So it provides you an optimized lower bound and upper bound solution, and it's based essentially on the work of the late Scott Sloan. It's very useful, and of course it gives you a solution which two sets of solution with bound the theoretically correct solution. For instance, you see here that by loading an abutment in the longitudinal plane, we ended up with a surface which has a rotated elliptical shape. You can see, for instance, that if we load in this direction, we get this maximum force, which has an horizontal and a vertical component, and this kinematic plastic mechanism. Whereas when we pull it away in the other direction, we obtain this small force here, pointing to the fact that, as expected, being an alternating structure, this system has a strongly asymmetric behavior. Okay? Its capacity is larger in this direction, it's intermediate in the other direction, and when you pull it away, mobilizing active conditions, it is the lowest. Okay. Of course, this applies to foundation, to abutment with shallow foundation, but we found that it applies also to piled abutment. Of course, the dimensions of the ellipse are different, but the shape is pretty much preserved. So the equations are still valid. And here, perhaps you can see also what happens when we apply the transverse loading component. When we load in transversely, we get smaller and smaller section of this elliptical surface in a 3-dimensional force space. So of course, if we load horizontally, the capacity in the longitudinal plane diminishes. You may say some indication of the plastic mechanism that we obtained, and also the equation for the surface that we publish. Oh, okay. I will. I'm writing in the slides also not only the authors of the publication, but the DOI or any publication in such a way that it will be easier for whoever is interested to retrieve the publication. When it comes to pile foundation, things are a little bit more complicated because it is quite difficult to carry out a parametric analysis on a pile foundation because the meshes become very complicated. So we took an intermediate path. We did a limited number of analysis with the same limit analysis tool, which is Optum. But we also developed a simplified procedure, developing our own code, which is named Deepful. In fact, Davide named Deepful, which is in fact a MATLAB procedure which incrementally analyzes a given load path in force space. And this is a 5-dimensional force space because we have 3 forces, 2 moments, and we neglect the effect of the torsional moment about the vertical axis. So it analyzes incrementally each force space, and it combines usual solutions that are applied to evaluate the vertical bearing capacity and the horizontal bearing capacity for piles by taking into account the continuous evolution of the yield bending moment in the pile section with increasing or varying axial force. So it's an incremental procedure. You may see it as simplified lower bound solution. People in the pile community tend to see this kind of method as a simplified lower bound solution, in which, of course, the degree of simplification is really very much dependent on the quality of the simplified formulation for design that you insert into the procedure, but the procedure is very general. Another ingredient, so the first ingredient is a failure condition, an ultimate limit surface. A second ingredient is an initial stiffness of the system and an initial yield surface. Now, also this depends on the problem analyzed. For instance, for a bridge abutment, we built some continuous three-dimensional finite element models with open seas, in which the soil was characterized by the PDNY constitutive relationship by the El Gamal research group. Basically, excuse me, so I don't know what happened. No. Okay. And basically, this is strictly valid for coarse grain soil. So the reference characterization were with some case studies in which the foundation soils were coarse materials. And you can see that by loading in different directions, we get some conventional yield point, and essentially we assume that the yield surface is homothetic to the ultimate surface. And you can see here an enlargement of the first yield surface, and the tangent initial stiffness gives us the initial stiffness as small strains at the macro scale. Let me show you the kind of response that we are getting from this formulation, concentrating on the static response. So on the left, you have a monotonic standing loading. On the right, you have a cyclic standing loading. So we don't have inertial effects yet. Here, this is a comparison of the static response of the macro element, which is the yellow line, the orange line, with the static response of the large continuous model made in OpenSeas. And as you can see, that not only does the macro element capture correctly the response, but it captures correctly also the directional coupling, because look, for instance, on the on this picture here, you can see that we are loading downward the abutment, and the abutment not only moves downward, but moves towards away from the embankment. And you can see that this movement away from the embankment is captured by both the continuous soil model, but also by the macroelement. If we pull by vertical force, the hypothetical vertical force, the abutment, we get a heave, but we still get movement of the abutment in the same direction that is away from the embankment. And you can see that this is called thanks essentially to the flow rule of the plasticity that is inserted into the macro element formulation. And you can see that on the right you have cyclic loads of increasing amplitudes, and you can appreciate that the macro element is able to follow quite closely the results that we have on the large continuum model. So this is a first static validation, but then we have a very important thing, which is the inertial response. Now, the inertial response implies that the behavior of the system becomes frequency dependent. So a way to see that for the large continuum model is to load cyclically the model with 4 cycles which vary in amplitude and in frequency. And on these plots on the right, you see a variation in the period that is a frequency of the forcing action. And you can see the amplification of the displacement. So when you go to large periods, you get a static response. When you go to periods which are, you see, of the order of 1 second, half second, which are well within the frequencies of interest in seismic engineering, you can see a significant amplification. You can appreciate that simplification, this amplification in this case, is captured reasonably well by calibrating one or two masses. So this is perhaps all that we need. The first mass, or sometimes the first and the second mass, meaning that either single mode response or bimodal response are generally adequate to reproduce the inertial response of the system. Now the problem is how one could calibrate this mass. Then we come here to the calibration procedure, because of course the results that you saw in the previous slide, they refer to this large finite element model, which was carried out for the development purpose. As it comes to calibration, we developed a set of theoretical analytical solutions that provide you the modal analysis of an embankment. And by knowing the modal response on the embankment in the transverse and longitudinal direction, you can derive analytically the first the modal vibration periods, and therefore knowing the static stiffness, which is the initial most strain static stiffness, it is possible to back calculate the masses that gets activated for each mode in each direction. For pilot foundation, we developed a different strategy. So we took advantage of the dynamic impedance functions that are available in the literature for an elastic system. And for instance, these are conveniently collected in this commercial software, very common software, which is called Dyna6. And for instance, this is an impedance function for this pile group. And this impedance function has a minimum. Theoretically, it must have a minimum because the minimum of impedance function corresponds to the maximum amplification. And so when by working out the minimum, the abscissa, the period corresponding to the minimum of the impedance function, we get the vibration frequency of the system, and the asymptote at large periods of the impedance functions is the static stiffness. And again, by combining static stiffness and vibration period, you can back calculate the masses. In this case, it is essential to sum the participating mass for each vibration mode to the corresponding mass of the raft, because these solutions do not include the mass of the raft, and in this case, the mass of the raft that links the top of the pile is very substantial. Meaning that you have the entire mass of the raft for translating modes, and you have the second moments of mass inertia for the rotational modes. A couple of things about validation. This is some validation of the macro element for the foundations compared with little experimental database existing. This is, for instance, centrifuge experiments done by the group by Luca De Santis in Cambridge. And this is a comparison with a three-dimensional finite element done by this other group, where we see that the comparison between the macro element response and the either experimental results or numerical three-dimensional results at the mesoscale, that is in a model that relates strain and stresses, is quite good. It is very interesting to see some validation in the, because the previous validation was for static loading. This validation here is for seismic loading. This is a validation that we organized in this way. We took a model bridge in OpenSys, and we imagined to have a preliminary design of this bridge with fixed constraints. So with this analysis, we got time history of forces at the contact points in which are relatively large, but this is an hypothesis in which the contact points will not deform. This is just to obtain some realistic force histories. Then these force histories, which is a three-dimension force histories for each element, were applied to a continuum large model or to the same to the macro element that represent the same system. This system here, I think that has something like 7,000 degrees of freedom. This system here is a zero-length finite element implemented by Davide Gorini in OpenSys, which in fact has 3 degrees of freedom. Okay, so this is the equivalence: 7,003. Okay, and this is the comparison between the time history of the displacement in the longitudinal, transverse, and vertical direction, and this is the force displacement relationships. We think that the agreement is very good. There is always some discrepancy with the vertical displacements, but in fact for the vertical displacements we do not particularly like the constitutive model implemented in the continuum elements, which has a tendency too strong a tendency to contract under seismic loading. So in fact, we believe more to the macro element results than to the continuum model results, but qualitatively the agreement is still quite good. And now we come on how to use these results. So a first thing to make, the important thing to make this approach to be used is that it should be available somewhere. At the time, for the time being, it is has been implemented in OpenSys. So we have zero-length finite elements implemented in OpenSys for abutment, for pile foundations, and also something for shallow foundation, which is more common. So these are in the process of being approved by the OpenSys routinary assessment, but they will become available soon in the open source code. Then they must be calibrated, and it will be rather lengthy now to show how they are calibrated, but essentially they are calibrated on 2 ingredients, because the idea is that you can, in a real problem, you are able to estimate capacity as well as initial stiffness. Capacity you estimate through the usual design structure procedure, because in design you must assess the capacity of your system, because you have to do your limit condition verifications. So you know the bearing capacity of the pile, bearing capacity of the group, the bearing capacity of the foundation. The other thing is that you can estimate the initial stiffness by the usual elastic solution calibrated on the small strain elastic stiffness, and the initial effect is obtained by these masses, which are evaluated through the procedure that I outlined before. So once you've done that, the idea is that 1 mass probably is enough for each degree of freedom. So 1 for each translation mode, 1 second moment of inertial masses for each rotational degree of freedom, and these masses are attached to the macro elements. So these are not inserted into the constitutive equation, but are attached externally. It's very easy to do that in OpenSys. And then once these macro elements are calibrated, there is a static stage which already includes the macro elements and provides the initial force state within the macro element. And then there is the dynamic stage in which a free field motion, remember this is a decoupled analysis, is applied to the endpoints on the of the macro element. That is, macro elements are attached to the structural node through the proper connection, bearing devices or whatever, and the seismic portion is applied on the other side. We can apply different ground motions to different macro elements to account for different ground motion resulting, for instance, because the piers have different lengths, or because there is a lack of synchronicity of the on the ground motion. So this is very general. Okay. The important thing to understand is that once you have a structural model of the bridge, the inclusion of these macro elements adds a very small computational demand to the analysis, because you add only a very limited number of degrees of freedom. Of course, there is a lot of non-linearity considered there. So in each calculation step, you need more iteration. So the computation time elongates, but not that much. And in fact, we were able to apply this procedure for a certain research project, which I don't have time to talk about, but that actually included the time domain analysis with nonlinear structural elements and nonlinear solid foundational element, that is the macro elements that involved between 2,000 and 3,000 OpenSeas analysis in time domain. And it was feasible only because these macro elements include nonlinear effect, but the computational advantage is enormous. And this is an example, for instance, and just to show you the kind of results that we get concentrating our attention to the foundations, is that you see here we have the time history, the longitudinal force, vertical, the longitudinal displacement for the left abutment, for the right abutment. These are very different because the one abutment was restrained to the deck, the other was free to move. You only have a simple bearing. Okay, we have the force displacement in the longitudinal direction for the piers. We have the transversal force displacement. So we can have the maximum forces, the maximum displacement, the permanent displacement in all the directions. Okay. And for the piers, we have the moment rotation relationship and the final, the maximum moment and final rotation at each pier. Okay, so we get this kind of information after a single analysis in time domain with a given set of seismic records. I say set of seismic records because for the same event, the records may be different because of the different positions of the contact elements. Of course, summing up some comments about this approach. On the one hand, we have that this is a very efficient way to analyze system, to include explicitly nonlinearity in a time domain analysis, because they are implemented, they are in there, they are in the software open source, they can be calibrated quite easily, they have had a very good validation, and they are computationally very efficient. They provide directly, what do they provide? They provide the maximum transient and permanent deformation, meaning displacement and rotation, where there is a moment connection. What they do not provide are, of course, what they do not model, that is the internal forces in the structural elements, meaning that at the end of the analysis, it is always necessary to go back to some local substructural model with an information. And this information is, for instance, the maximum force that is here, the maximum force. And if you have this information, maximum force, if you go back in your all the maximum displacement, it really depends on what you have to design. With this information, it's relatively easy to calculate in a local model the maximum internal forces in the structural members of your abutment or in the piles, so work out the plastic deformation in the piles. But you require a further model, which usually is the model that you have been using in order to design in the first place the foundation. Now, I think that I have 20 minutes or 25 minutes more to talk about a different method. Different method, this is a partly coupled method. Essentially, it's a method in which we take a completely different view. We take a numerical representation of our problem, but we understand that its dynamic response will be influenced by the structure that is connected. By the structure that is connected to the foundation element. So we must mimic in some way the dynamic response of the structure, and our goal is to include the dynamic response of the structure into our local soil foundation simulation. Now, a way to explain this is to start from really where it started quite a few years ago. It started when I was in a certain way involved into the seismic verification of the Messina Strait Bridge. I recall you that the Messina Strait Bridge is going to be the largest suspension bridges world. The central span is more than 3 kilometers. Since you know very well that the design of this structure has been is more than 50 years old, but every time the designer had to complete the design, they should complete the design in 2 months. At a certain stage, the designers needed to make a final assessment of the design, considering explicitly the soil structure interaction for the bridge. You must understand that suspension bridges, especially large span suspension bridges, are not very sensitive to the earthquake, because their main structural elements vibrate at very long periods that do not overlap with the frequencies included in the seismic acceleration. But for the substructures, to get the local displacement of substructure, some effect may be there, and of course there is a very important seismic source just in the close proximity of the bridge. So the idea here was to I'm representing here the Sicily side. I just now I'm just thinking now that perhaps this is a mistake, because being where I am now, I should have considered the offside shore. But I will tell something about the offside shore. But I'm sorry about that. No, the idea is that it was at that time to have a smaller model, taking advantage of a peculiarity of suspension bridges or large span suspension bridges, which is that the behavior of the several contact elements, which are 4 contact elements, the 2 towers and the 2 anchorages, are dynamically decoupled from each other. Because if you look at this, which intends to be the Sicily Tower, the Sicily Tower is connected to the Calabria Tower by a suspension system on which the principal suspension cable vibrate with a period which is between 20 and 30 seconds. Now, in earthwork engineering, 30 seconds means that this is a static constraint. It's one of the few cases in which you can attach something to a fixed point in earthwork engineering. Okay, so what we did was to develop a simplified representation of the tower in a series of two-dimensional, in that case, flak analysis, in which we developed simplified dynamic models of the tower, which were connected through a series of masses and springs to fixed points. And these masses and springs were calibrated in order to reproduce the modal shape in each direction. This is only the longitudinal, I believe, of the tower, and also the main frequency response. In principle, this should be done through a modal analysis. Flak does not have the capability to carry out a modal analysis, so this was carried out implementing a frequency sweep and concentrating on the instant of maximum amplification and looking at the non-dimensional deformed shape. Just to tell you the kind of results that we got this is a time history of acceleration of given accelerogram. This is a time history of the longitudinal displacement and the tower and then the block. The block, the story was simpler. The block, it was they were just subjected to the force cable, which was constant in time, because again, this was provided by a cable which was vibrating with a very long period, and we get the time history of the rotation at the base of the tower, and this is an indication of the permanent displacement on the performance of the foundation. But these time histories were inserted back at the base of a global structural model to carry out a dynamic analysis, a dynamic structural analysis with enforced displacements and rotation at the base to carry out a dynamic analysis that already took into account implicitly the soil structure interaction, because these displacements and forces were coming from this simplified soil structure interaction. You see, you can see the permanent deformation of the several contact points: Sicily block, terminal structure and tower, Calabria eventually tower, terminal, structure, and block, and the end of this analysis. A similar but a little more complicated analysis was done to analyze a different suspension bridge. There's been a time in which I was very much into suspension bridges because these are very simple to understand from a non-structural specialist. So I came across to this project in which, in fact, I was asked to do an internal validation of the design. So it was an internal audit done by the Danish designers of this bridge. And this was interesting because these are, here in Turkey, this is the Izmit Bay Bridge. On the northern fringe, on the western fringe of the northern Anatolian fault, very close to the epicenter of the Izmit earthquake. So there was a strong concern about earthquakes in this case. And so strong that the foundation, see the foundations here are at the seabed. The foundation was endowed with a dissipative device, which is a gravel pad. So the foundation piles, which are driven piles, are not attached to the caisson. I think that I had, okay, to the caissons, these are the caissons. But in fact, it is detached on purpose. There is a thick layer of gravels that acts as a fuse or as a frictional dissipative device. So there was also some concern about how this device will be actually working under an earthquake, because should be said that this design detail was in fact copied by a different bridge, which was the Rio-Antiron bridge in Greece, that on the other hand was a cable-stayed bridge. It was different, was much stiffer. Okay? Now, I won't tell you how the design procedure will did end, but I'll tell you about some study that David and I undertook a few years ago, because we were very curious to see how this frictional device will work, and we had the data for this project. So we concentrate here on the North Tower. In the North Tower, you see the scheme of the foundation. You see that the soils, you should see the left column here, are a sequence of silty clay, clay silt, sandy silt, and then N4 is a medium stiff clay. And at the depth of the 180 meters, there was a sort of bedrock. It was really an argillitic bedrock with this shear wave velocity, which was slightly less than 800 meters per second. I'm going to shorten significantly the story for you today. So we developed a three-dimensional model in FLAC of the Northern Tower. And again, this Northern Tower is has a simplified structural model which is connected in some way with the anchor blocks and with the other tower. You see here the free field boundaries in FLAC here. And of course, this could not be so detailed, but the PIs are always a problem to model in detail. We decided to regard the pile group as an equivalent foundation that was given a transversally anisotropic behavior through a homogenization technique. The simplified structural model is a little less simplified than before, because now you have the tower, which is reproduced pretty well in the FLAC analysis. You have a system of masses that represent the participating masses of the main cables. You have springs that represent the stiffness of the cables in the longitudinal and in the transverse direction, because a tension cable is stiff also in the plane, in the orthogonal direction of the plane in which it bends. And then we had that the deck was connected rigidly to the tower in the transverse direction, but it was not connected longitudinally. And we simulated that by this pendulum here, which were rigidly connected transversally, but longitudinally connected with a spring that represents the stiffness of the deck. And this model, in order to work, needs large deformation, because it's a secondary suspension system. Therefore, this pendulum changes its actual force as an effect of the change of shape, because it declines, and within its length, the force traveling here has a horizontal component. So this needed to be a large strain analysis. These are comparison between the model deformation for the two models, the FLAC model and the global bridge model, which is a structural model. Few more details just for sake of curiosity, that when you do such a thing, there are a lot of other information that you need to add. For instance, how to model the interface, how to take into account that the interface is submerged, how to compensate for the pressure of water, also how to compensate for additional masses, because of course in the structural model we were able to insert only the masses that participated to the first mode. But of course, these are not all the masses that the tower is called to carry. So we needed to but we needed to get the effective stresses right in the subsoil. So we needed to apply some compensation pressure here for forces with no mass, otherwise to suppress the initial response. We had to implement a homogenization technique to develop this continuum equivalent with the transversally anisotropic response. But I'd like to show you some results, because these are elastic spectrum of accelerations. This is one of the basic input. This is a well-known record, DABAS record, a very strong record that was representative of the no-collapse limit state. You see, and this dashed line here is really the response of a free field ground response analysis, which was cutting down all the acceleration amplitude because it was causing a rupture in the free field soil. What we got was instead the thick line that, as you can see, at the large frequencies is characterized by some de-amplification, but that in the soil foundation response range, it's has still relatively large spectral ordinates, and it produces some amplification in correspondence to the vibration periods of the tower models. And so the response was completely different from what we could have got from a free field analysis. And this is really why this coupled modeling was implemented. Another important thing is that here. You here have the time history of the displacement at the contact with the interface. Okay? See that we go from 0 to 4 centimeters, more or less, with a permanent displacement maximum of 2 centimeters. And these three analyses are analyses that consider, in turn, only the longitudinal response, the longitudinal and the vertical response, and the three components of the seismic motion. So you see here that it is necessary to take into account all the components. Otherwise, we underestimate the relative displacement along this dissipative interface. And it is instructive to look at this plot in conjunction to this, with this other plot, where you can see that the larger the relative displacement along the interface, the smaller the spectral ordinates. So in fact, when you have a large energy dissipation along the interface, you transfer to the structure smaller forces. Okay, so this is the way in which these dissipative devices work. They dissipate energy, and then less energy goes up into your system. Okay. However, when we looked at the displacements of the caisson relative to the bedrock, we ended up with maximum instantaneous displacement of 60 centimeters, and that's okay, but with the final displacements are about 12 centimeters, meaning 5 to 6 times larger than these ones. So this permanent displacement really did not come entirely from the dissipative interface. In fact, only for a small part, they were coming from the dissipative interface. But if you look at this section where we have contours of horizontal displacement, you can see that there is a zone here where gradients are larger, and this is a zone where horizontal relative displacement were accumulating. This can also be seen by this displacement profile, meaning that in fact the system already had a dissipative interface here, because the dissipative interface was made by the low strength of the foundation soils below the pile group. And therefore, this is where most of the energy dissipates. and what remains is only marginally dissipated along this dissipative interface. Okay, so in this sense, our understanding of this dissipative interface through this partly coupled model was that this dissipative interface was not perhaps strictly necessary, but it was a useful addition to a phenomenon that would have happened all the same because of the low strength of the foundation soils. This was built and opened very quickly because we're in Turkey and not in Italy. To conclude, just to tell you that we made some attempt to include a similar approach, so a partly coupled model in which we attach something which has more or less the proper dynamic response to a complete model of the abutment soil interface. Okay, I will not enter into the details. For instance, in this case, we developed for a certain bridge, which is this one in the complete model, a bimodal assembly of rheological elements that was calibrated dynamically and was attached to the structure of the model abutment. We get some interesting, although a little mixed results, in the sense that if we, these are elastic response spectrum of the motion accelerations at the contact between the deck and the abutment, that is at the head of the abutment. If we do not include any interaction, we just have the vertical force transferred by the deck to the abutment, we get that in this range we have ordinates which are too small if compared to those of a full model, which is green. If we apply this simplification, this simplified dynamic model, which is two masses, two couples of springs and dashpots, we have a quite close resemblance of the acceleration that are exchanged at the deck abutment contact. We get reasonably where the maximum forces. So what we don't get is the final permanent force that remains locked at the contact between the deck and the abutment, which is of course impossible to get because in this case these things are not attached to anything. So when the seismic commotion ends, for equilibrium, this can have no forces. But for the maximum force, it's okay. And also when we look at the relative error in terms of permanent displacement and what matters more, maximum forces in the structural members, because this is done to design the structure of the abutment and to evaluate its performance. The blue are with the structural macro element. We call this assembly or logical elements a structural macro element. With structural management, we have a very small error. Without considering this interaction, we have a very large error, especially on the permanent displacement and on the internal forces in the abutment, which are significantly underestimated. And we carried this study a little step further just in the last month, because we are publishing a paper now, in which we say, okay, but since we have a simplified representation of the structure, which is a structural macro element, and we develop a abutment macro element, let's put them together. So let's have a double macro element approach in which neither the soil nor the structure is already there. All the response is encapsulated into these two zero-length finite elements, and you can see that in fact we get the same response. And these analysis, of course, runs in a couple of weeks. This analysis runs in a couple of minutes. Okay, and at least longitudinally, it gives you essentially a good response. As usual, in this case, having a macro element to represent the abutment from the soil system, you need to get a maximal force, go back into the local model, and work out yourself the internal forces in the abutment. But I think it's a price that can be paid if the computational time is so short. Now, conclusions. First conclusion is that, as I told you before, we designers, I'm not a designer, but designers, have are and will be more and more called to this inconvenient task to design structure for very large earthquake that most probably will not happen on the structure. So they are called to predict out of the blue the performance of structure that are subject to very large earthquakes, perhaps sometimes not in a particularly earthquake-prone areas. I work in Rome, for instance. Rome has a low seismicity overall, but now structures in Rome have to be designed for certain limit states with significantly large acceleration amplitudes. Okay, in doing that, so this is because, as I told you, we have increasing expectations for people, for politicians, not increasing earthquakes. Okay, let's not confuse the two concepts. So therefore, we should be able to accept the tolerant damage, and therefore we had to make. I have been living this process for the last 20 years. Our seismic actions are always growing. No one takes the responsibility of reducing the seismic actions by law because we want to be protected by extreme events. And the only way out is to have models which are more and more realistic. Because if you apply a large seismic action on a conventional system, it will be conventionally fail. Okay, so we must represent the entire process. Our models need to be more and more realistic. But on the other hand, design cannot be based on complex models because design needs iteration. Any of you who's been involved in design operation knows that the design choices are made on simple calculations because you need to make iterative calculation and adjust and check and spend a little less and modify the technology and what else. So therefore, probably how simple our models should be. This is probably the main question. Perhaps we can take inspiration about the famous sentence inspired by which is ascribed to Einstein. Nobody's really sure whether this is true or not. We say that everything should be made very simple, as simple as possible. We simplify, we simplify, we simplify. But then there is a simplification level where our simplifications sort of touch the bottom. And if you simplify further, you make a naive system, naive model. So where does this our simplification do touch the bottom? Well, we've seen that for us, non-linearity is an essential feature to comply with the design needs that I'll be discussing. So perhaps everything should be made as simple as possible, but not linear. Thank you very much.
Thank you. Oh, okay. Thank you, Professor Callisto, for the great presentation. It was really good and really enjoyed this presentation. I would like to open the floor to questions. If we have some from here. Yeah, do we have? Oh, we can, if you have questions from online, you can just raise your hand and then unmute yourself, or from here, just let me know if you have any question. Yeah, there is a question from here. If you can come here, otherwise online.
Thank you so much. Thank you for Professor Callisto for this amazing state-of-the-art presentation, not just a seminar, which was really inspiring. I have a couple questions. Maybe we can talk about a little offline. The first one is about the calibration of the initial stiffness of the system that you were showing. We know that oftentimes nowadays we have a lot of new data that's been collected, especially from non-destructive tests, including HVSR, horizontal to vertical spectral ratio, which I think may inform that portion of the calibration. So I was wondering whether you've been using some of the data, if some of the data that I'm talking about was available at your case studies, if you did make some use of these data to inform the calibration process.
Not particularly. My view is that these are relatively simple problems, but not that simple, in the sense that these are time domain analysis, and I think that some direct evaluation of the soil stiffness is necessary. Also because we are talking here about the stiffness of the soil volume that interacts directly with the foundation. So we should have a tool that is able to characterize directly that soil volume and not an overall deposit from which we just know the first vibration, the fundamental vibration period. Also because the fundamental vibration period given by the HSV, if correct, that is the overall vibration period of the soil deposit, they may have nothing to do with the vibration period of the soil volume interacting with the foundation, because we need the local measurements. And of course, when it comes to bridges, hopefully to bridges of a certain importance that warrant the time domain analysis, probably it is the case. So preferably a cross-hole test or perhaps a downhole test, but little less than that.
And then just one more curiosity, which is about, I think my understanding is that excess pore pressure development is not part of the model. Do you believe that there may be an extension of the framework whereby you can simply add it as a feature? Because the entire framework is very pragmatic. So seems like it will be one thing to try.
Absolutely. In fact, we have a PhD thesis in progress which should be dealing with this. There will be so many things to say about this, but I won't, in part because I'm not yet sure, but a couple of things. In fact, my impression is that there may be a way to insert the effect of excess water pressure at the macro scale. For instance, I myself did something to that effect, which is not yet published for retaining structures at the macro scale. That is essentially constitutes a sort of damage law, let's say, to the constitutive response. But in fact, in my humble opinion, we are not able to design nothing today in the presence of pore water pressures, even without a significant accumulation of excess pore water pressure. When I found myself in writing the Eurocode, they say, okay, let's write something how to design a foundation in sand. When the sand is saturated, it was very strange. We could not come out with anything sensible, like a total stress analysis sand. Where do you find the total stress analysis under cycling condition? From liquefaction, but liquefaction is in the free field, whereas you have interaction. So yes, it's a problem which is very, very present in my mind, and together we look forward to incorporate it into our macro element. We have some ideas, but we still lack the at least numerical evidence, but extremely important.
Thank you. Do you have any other question? Do we have questions? Oh, yes.
Taking into account so linear and non-linear behavior of the soil is a fundamental aspect in the soil structure interaction. But in general, some researchers thought that non-linear behavior of the soil tends to reduce soil structure interaction. The results presented show that it's not so. Nonlinear behavior of the soil does not reduce soil structure interaction effects.
To answer honestly your question, there is no increasing or reducing soil structure interaction effect. There is changing the dynamic response. Now, a change in dynamic response can be beneficial or can be detrimental, really depending on several things: the structure you are examining, the frequency content of your seismic motion, and also the performance quantity that you are looking to. For instance, what nonlinearity does not reduce are the permanent displacements. If you have a linear system, you have zero permanent displacement. If your system is sensitive to displacement, to permanent displacement, so nonlinearity of course worsens the displacement, and that can be very important because, as you can see, I've seen in the example of the bridge, you have an abutment that accumulates displacements, and under that displacement, the bearing device gets a significant damage, or perhaps the run of the bearing device is achieved. And therefore, that is a very important damage. So in terms of displacement, this is more or less always true. In terms of stiffness, it really depends, because in a linear range, you choose a stiffness, which is a secant stiffness, and a damping ratio. Out of the blue, are not really justified. So get a more realistic representation, I think, is the key. And then we will see what happens, whether it is better or worse. Hopefully, you will not even have a terms of comparison, because in my idea, you should go for nonlinear from scratch.
Okay, if we don't have any question from the online, looks like we don't. Okay, I would like to thank again Professor Callisto for being here. I know that he has a very busy schedule back in Sapienza, but I really appreciate him being here. And I will thank you everyone that is here and also connected. And I hope to see you all to the next webinar series. Thank you so much.
Thank you.